All right, so topic 8, circling back to circular motion. We got a few things that we should just remember from previous conversation about circular motion. So v squared over r is centripetal acceleration. Another way to express centripetal acceleration would be 4 pi squared r over period squared. And I'm not re-deriving these things right now. I'm just presenting them as facts that we can recall from the past. We got an alternative of 4 pi squared r times the frequency of orbit squared. And really the reason that those two are the same equation essentially is that period is 1 over frequency. So they're, with that little recognition, they're the same equation, right? But then we have this idea of centripetal force, which is what we're going to focus on today. So centripetal force, again, we may have said this once before, Fc, it really is kind of the equivalent, when I make this statement, it's the equivalent of talking about Newton's second law, but for circular motion. So I'm going to say centripetal force is mass times centripetal acceleration. And so when we calculate Fc, using those equations over the left-hand side, we'd say mv squared over r is Fc, m times 4 pi squared r over period squared is Fc, or m times 4 pi squared rf squared is Fc. And just a little note on this, let's make myself a little block off here, that when we talk about Fc, not only does it seem like an equivalent statement to Newton's second law, but for circles, it might be better to say Fc is the equivalent of stating F net, but for circular motion. And I one time had a student say that their sibling had come back from university saying that the first year professor had a rant about how centripetal force isn't like its own standalone force. It's not like gravitational force or electrostatic force or friction force or something like that. It's not that kind of a thing. It really is like F net, but for circles. And so I'll do like the preemptive rant, I guess, right? So next year some professor might have that same rant at you, but you will have already heard it once, okay? And we'll kind of see it in action here. Really quickly though, let's do some basic, like, can we plug in the values kind of things. So I got a race car that travels around a flat circular track with a radius of curvature of 80 meters at 20 meters per second. The car's mass is 1,000 kilograms. All right, so in terms of our givens, if we were going to find the centripetal force acting on the car, the mass is 1,000 kilograms. The speed instantaneously would be 20.0 meters per second. Radius of curvature is 80.0 meters, and it's going around a flat circular track. But you know, in our everyday lives, we might have situations where we have, you can imagine, like a road system. Oh, I'll bring it on camera. A road system that looks like this, and we have these curved on-ramps or turning lanes or whatever it is, depending on, you know, the local highway setup, right? And of course, those kinds of curvatures would have a radius. And so in terms of how we would use this kind of thing in urban planning or like looking about how the roads work, would be to maybe think first about what we're going to do right now, but then you notice part B, there's something to do with friction. So we might talk about what kind of traction would be required on the road. So let's do this step first though, okay? So we've got our givens, and we can say Fc is equal to mv squared over r. Plug in our values, 1,000 kilograms, 20 meters per second, squared, r, 80 meters. And these are nice round numbers. 20 squared is 400, 400 times 1,000, that's a big number, 400,000, 400,000 divided by 80, we end up getting 5,000. 5,000 newtons. Now in terms of the significant figures, we've got 3 over here. So this is ambiguous. We could write a line right there. I personally like 5.00 times 10 to the power of 3 newtons as my way of expressing this. And people say, okay, so what does this force really represent? Well, if we have a car that's taking the curve, here I'll draw the curve. Here's the curve. Car driving around a corner. And this might be my moment by moment snapshot of this car taking this curve. I know, and I'll do it in red. I'll do the velocities, instantaneous velocities in red. Look, my velocity would be going like this at this moment in time, tangential to the curve. There, there. I know that that would be my velocity, but you know, and this was a student actually in the back right-hand corner of this room said, so like if you were gonna ride a bicycle around that curve and you weren't gonna steer, how would you, like, could you get somebody to take the corner? What if people like stood at this point, this point, and this point with baseball bats and like smacked you with a baseball bat here, here, and here? Would that keep you on the curve? And like even better, if you had people like 50 people around the curve smacking your bicycle with baseball bats, wouldn't it force you to make the curve? And extending that idea, what direction would they have to swing their baseball bat in? Well, of course, the answer is they'd have to swing their baseball bat towards the center, right? Like this person would have to swing their baseball bat this way. This one would have to swing their baseball bat this way. This one would have to swing their baseball bat this way. And with that thought experiment in mind, that tells us that centripetal force has to point which direction? Towards the center. Always towards the center. I mean, it's called centripetal force, towards the center. And so that Fc at any given snapshot in time is going to be the net force acting on that object toward the center. Okay, so the forces are always towards the center. So we can say, therefore, the car has a centripetal force of 5.00 times 10 to the power of 3 newtons towards center. Oops. And you know, this is something that I always remember when it comes to like language. And I'm no etymologist. And one thing that really bugs me about etymology is when people get it mixed up with entomology. But etymology is the study of words and entomology is the study of bugs, which is why that joke is funny. Now you can laugh, okay? Etymology and entomology and the mix-up bugs me. Anyway, centripetal. There's a popular word that we all know called petals of a flower. And if anybody's ever looked at flower petals under UV light, this is kind of a neat thing. All the veins, turns out you study entomology, the study of insects, and it overlaps with etymology in this specific case. That's why the joke is continuing to be funny. Now that I've explained it, you can laugh again. Ha ha ha. It turns out that the circulatory system of flower petals points towards where all the good stuff is in the middle of the flower, almost like a landing guide for bees. And so these guys here point towards the center. Petals have a center guidance system for insects. Centripetal, towards the center. Please don't get that mixed up with centrifuge. A centrifuge is the effect of things with more inertia or more density drifting towards the outside of a curve. And that actually is caused by inertia. Okay? So let's make sure that we know the difference between the two. A centrifuge effect is an inertial effect. More dense things get pushed towards the center, or they appear to get pushed towards the center because of their tendency to go tangentially off on a straight line from a curve. Whereas centripetal is pointing towards the center. All right. So with that little language thing out of the way, please don't forget flower petals. Flower petals point towards the center. Really easy to remember. Centrifuge versus centripetal. We're only talking about centripetal forces. Centrifuge effect is not a true force. All right, so what's the minimum coefficient of static friction that allows this car to stay on the path shown? Well, again, let's do like a quick overhead view. And I've got myself a circular path here. Oh, that's not a very good circle, but it's a circular path. We've got a car that's going to drive, that's a terrible car, along the circular path. Again, I'm going to use red to indicate velocity because I don't want to get mixed up with forces. So there's my velocity. And what we're claiming is that the centripetal force is pointing towards the center of this circular path with a radius r. Now, if I were to be looking at this car here, let's just give the car some taillights. If I were to look at that car as it drives away from me, the car would look like this. Here's the same car, but looked at from behind. Here's its wheels. Give it some taillights. Cabin for the humans, okay? And as this car drives away from me, notice it's driving away from me. So I'm just switching my perspective to a rear view, overhead, just so we're not losing ourselves. Overhead, rear view. Okay? I know that there's going to be an FG down. And if we're on flat level ground, there's going to be an F normal straight up. And then what I have to fight myself from saying is FC towards the right. FC should not be attached to this picture. What's really allowing us to have the centripetal force is a static friction force. And people say, well, the car is moving. Well, yeah, it's moving, but is it sliding? It's not sliding. The wheels, think about how a wheel goes around a corner. Does it have lateral sliding? No. It wants to stay grippy. And you can read more about how tires make grip, right? Like the whole traction and tread thing. But for now, let's just say it is static friction force, for sure. There's no kinetic friction force sliding a car around a corner. We, by design, want it not to slide sideways, right? And so what must be given this horizontal inward force is got to be the static friction force. I mean, by virtue of the fact that we steer our front wheels, probably, right? But it's the static friction force that's supplying that traction, right? So at most, I can say that that free body diagram is equal to FC. Remember what I said before, FC is circular motion, net force. Yeah?
Is the FS going in right because you're turning right?
It is, yeah. So at that snapshot in time, the FS is going towards the right. At a later snapshot in time, like up here, the FS would be going southward, I guess, if we're using that reference frame. Okay. All right, so back over here, we got our free body diagram. So I want to make a quick little note. If I want to be able to, at a minimum, notice, minimum is a key word here. At a minimum, my static friction force has to supply that FC. Okay, so at a minimum, I would say that FC has got to be equal to mu s times Fn at a minimum. Can the mu s be more than enough to make the turn? Yeah. In fact, by design, we usually do want it to be more than enough, which is specifically why people put speed limits on turns. You notice like in the winter, they have icy in winter. Minimum speed shifts down to whatever lower speed it is so that you can make the turn in order to accommodate the requirements for this. But let's do some figuring. So we know that FC is equal to mv squared over r, and at a minimum, this value and this value will be equal to each other if we're going to be able to make this turn. So let's bring them together. So mu s times F normal is equal to mv squared over r. This would be the minimum coefficient that we would solve for in order to make this turn. I could put in has to be greater than or equal to. So right there could be a greater than or equal to sign, but that wouldn't let us solve it, right? So the coefficient of friction has to be greater than or equal to the value we're about to solve for. All right, so we can pop up to the top here and we can say, all right, well, if I solve for mu s is going to be equal to, oopsie, sorry, I miswrote something because I was thinking about my next step. mv squared over r, all divided by Fn. We know that in this situation, the normal force would end up being equal to mass times acceleration due to gravity. So mv squared over r divided by not Fn, but mass times acceleration due to gravity. Because remember, absolute value of that Fn is going to be the same as that guy. Now, people that are really committed to this will say, hey, look, that really is mag over 1. So we really have a fraction over a fraction here. So I could simplify this out to say, well, mv squared over r times 1 over mag. And you're like, oh, sweet. What cancels out? Masses cancel out. Gone, gone. And it turns out that in this case, we could say that mu s is equal to v squared over AG times R. Clean this up just a little bit. That's our mu s value. And it's mass independent. That's kind of nice. Could we have calculated the FC first and calculated the FG second and then divided FC divided by FG? Absolutely. But this is another example of where generalized equations, or like keeping the variables all alive as long as we can before subbing in, makes our life just a little bit easier. And I really do want to sell that idea, right? Like I think that if we can keep our variables alive as long as possible by using systems of equations and subbing one into another, this is bread and butter kind of territory for us. We should be able to make a living on this. So mu s is equal to, what was it? 20 meters per second? Don't forget to square it. Divided by 9.81 meters per second squared times the radius of curvature, 80 meters. And 80 meters, I mean, let's be realistic. That's actually a really big curve. That's like highway off-ramp, like a big highway off-ramp even. Maybe even a highway interchange from one highway to another. Can somebody help me out with the math on this one? Because I don't trust myself. We got trust issues with me. I've let myself down in the past. Yep. 0.5096. I love it. Got anything else dangling after the 6? 6, 8? Yeah, so that could go up to a 7 if I was going to stop at the 6, right? Okay. That's what I was concerned about. All right, and of course we only got 3 sig figs, so this is going to end up being, annoyingly, 0.510. And remember, there's no units. Now, with all these units, it's hard maybe to immediately see that it's unitless, but we could just do like a quick little dive into this one. Meters per second squared is going to be meters squared per second squared divided by meters per second squared times meters. Notice that the second squareds are gone. That's meters squared, so the meters squareds are gone. It's unitless. Okay, so once again, coefficient of friction, regardless of if we're in circles, coefficient of static friction has got 0 units associated with it. Now, another direction that we could take on this one is if you knew, yeah, we could do a therefore statement. Therefore, the minimum, oh, that's ugly, minimum coefficient of static friction is 0.510. But just a second ago, as I was trying to derail my own solution, I could say, hey, listen, yes, Lynn? Well, that's a good question. So with this one here, we don't need a reference frame really yet, because we're not asked for a direction. But as we work along here, we could have said a north, south, east, west reference frame, but notice that the mu s was always just going to be a magnitude without units. So it didn't affect things. Even the normal force when it came in was going to be just an absolute value. So in this stage, we really didn't need a reference frame. We could say with this previous one that we have a north, south, east, west reference frame, but even then, based on the particular question that we were solving, it was always going to be towards center. So situationally, let's be choosy about how we use reference frames. We will use reference frames with circular motion today, though. Now, in a what if you were told, that it wasn't the minimum value, 0.5. What if we were told that mu s equals, I don't know, 0.95 for the average tire to road contact. And this might be something that people would want to know. The coefficient of friction for the average tire to road contact for, I don't know, whatever the most common tread is out there, right? And remember, we want to make sure our treads don't go bald. We want to make sure that we test for tread depth, all that sort of thing. And if you're in auto, you know that that's an important thing. But even if you're not in auto and you're going to be a car owner, you should be checking for tread depth, or you should you're going to have that checked if you don't know how to do it. Honestly, look up what a good rule of thumb is on the internet. There's usually a lot of people with that. And if you can take a penny or a nickel, and you can, I guess we don't have pennies anymore, nickels or dimes, you can insert that into the tread, and you can get a good gauge of how deep your tread is, and measure how deep that depth is off of the nickel. Because it's hard to take a ruler and stick it in, and oftentimes we have loose change that you can stick into your tire tread. It's a really easy way to check this, right? So look for what the standard tread depth should be for your car for the season that you're driving in. But anyway, if we did know that this was a desirable average tread coefficient between road and tire, could you figure out what the maximum speed should be before slippage? Well, sure. Now that we've got a general equation like this guy over here, notice that this equation is not mass dependent. So when I said that this is the coefficient of static friction between rubber and a road, I'm not saying truck, car, minivan, whatever. This is just rubber in the road, you know? If this was the coefficient of friction between rubber and road on my local roads, I could calculate for a given radius of curvature for off-ramp, on-ramp, turning lane, whatever, I could figure out what my minimum speed should be. And then as a civil engineer, I'd go around and I would make appropriate signage, right? And you would usually say that the speed should be slower than what it actually is, because then you sort of like psychologically condition people to be safer than they need to be, you know? Because we don't want people to die. And if you've ever driven, you know, you ever been to like a cliff's edge and there's a guardrail that's dinged because somebody took the curve too fast? You realize like exactly how big a deal this is, but you don't have to go that far. You can just look at the off-ramp in the local highway and you can see that that metal, you know, guardrail has been dinged because people are exceeding that speed for the given coefficient of static friction. They're going off the road. I mean, it happens mostly in the winter around here, right? I mean, truthfully, most civil engineers, most road maintenance people are going to over-engineer it. My own grandfather was that was my uncle was Parks and Rec. My grandfather was roads maintenance for a region in the Niagara area, and at the time, I mean, he had like a grade 6 education. He went through elementary school, and he was a local person. He was a hard worker. He was given the job, but at the time, rather than having engineering degrees, what they would just do is change the texture of the road. They'd rough it up. They'd make sure there's lots of gravel in the tar to try and drive up this value to keep people from skidding off the road and killing themselves in the winter, right? And so we still kind of think that way. We might be a little bit more engineering about it, a little bit more statistical about it than Grandpa was back in the day, but the same principle is there. We're just trying to rough up the road, drive this value up so that people can take corners safely, right? So some of you guys are going to be engineers. That's something you may have to think about. Anyway, so I'm going to move on from that.